Let's continue with our lecture on mathematical methods. We have been looking at the partial differential equation in physics. We have seen wave equation in one dimension. Let us look at some of the important application. Today we will look at the Laplacian in the spherical polar coordinate system. Uh, we have already seen the Laplacian in the plane polar coordinate system, and here we extend it to spherically symmetric cases. The Laplace equation in a spherical polar coordinate system. This is a part of course PH3103 at IISER Calcutta. Laplace equation in spherical polar coordinate system. We use a spherical polar coordinate system r theta phi. The Laplacian in this coordinate system is given with this messy expression, which is given as a 1 by r del square by del r square r psi plus 1 by r square sine theta d by d theta into sine theta d psi by d theta plus 1 by r square sine square theta d square psi by d phi square is equal to 0. We will not get into details of how to derive the Laplacian in the polar coordinate system. Let's simply use this as a definition and get on with solving it using our method. So when we have a first differential equation given, we have to look at each term very carefully and see whether the differential operator given there are familiar to us, whether we know the eigenfunction of these differential operator. Now this equation is somewhat badly written. It looks like r, theta and phi are all getting mixed up. Of course, in this system you can see that the coefficients of differential does not depend on the function phi, so which is leads to the symmetry. However, rest of the variable r and theta are seems to have got mixed up with each other. By looking at this equation, it is obvious to see that we have 1 by r, 1 by r square and 1 by r square multiplied to each of terms. So one of the straightforward thing to do is multiply it by r square and obtain the equation in a somewhat neater form. So after multiplying r square, we get first term as r into del square by del r square r into psi plus theta term, which seems to be now separated from the r term, as a 1 by sine theta del psi by del theta into sine theta into del psi by del theta plus 1 by sine square theta del square psi by del phi square is equal to 0. Now, of course, phi term and theta terms are mixed up. Let's try to see how we can proceed. Now let's look at the differential operator. This seems to be familiar differential operator, and we also know the eigenfunction of this differential operator. We know that the e power plus or minus im phi is the eigenfunction of this differential operator with the eigenvalues as a minus m square. So we can straight away use this to simplify this expression. We know that we have to do this term by term rather than separating and then expand in terms of the orthonormal polynomial. So that is where we have to identify all the terms in the differential equation. In this case, m should be integer, otherwise the function won't be smooth when going from 0 to 2 pi. Now, let's look at this differential operator, which also looks familiar. We have used a similar operator, which is we call the Euler operator in the plane polar coordinate system. This is slightly different than that if you have carefully looked at it. In this case, we have a r into del square by del r square. As it is, we are not familiar with the eigenfunction of this. In such case, it is good to start with the r to the power L, because we have already seen a similar thing work out in the case of plane polar coordinate system. Let us substitute this in this term, and we see that r power L become L plus 1 inside the differentiation. We differentiate twice, we get a L into L plus 1 into r power L. So r power L is one of the eigenfunction with the eigenvalue L into L plus 1. Now extending this to the minus power, that is r power minus L, seems to lead to somewhat different terms. That is, in this case it becomes r to the power minus L plus 1, and then we differentiate it, we get L minus 1 plus 1 into L minus L. So that is somewhat different than what we have. We may need to change this form when it comes to negative powers of r. So let's try with the next thing is r to the power L minus 1. So if we inside the differentiation, we see that it becomes r power minus L, and then we differentiate it twice, we get L into L plus 1 into r power minus L minus 1. So again, this is a eigenfunction with the same eigenvalue L into L plus 1. So these two eigenfunctions are convenient. So we can state that the eigenfunctions of this differential operator is a r power L and a r power minus L plus 1 with the eigenvalue as a L into L plus 1. Then we need to substitute these in terms of our differential equation. We have two eigenfunctions which we have to expand, and then see what kind of a differential equation is left out for the theta term, and then we have to simplify. All this looks somewhat cumbersome. For going any further, let's try to make an assumption in order to simplify. Let us assume our system is actually or azimuthally symmetric. That means that our solution psi does not depending on phi. So it depends only on the function of r and theta. So such kind of a physical system we call the azimuthally or axially symmetric system. So it's also quite important in the physics. One of the most common symmetry which we use is a spherical symmetry. That means your physical quantities psi depend only on the variable r. The next generalization we have is a function which depends on r and theta and independent of phi. Such systems are actually symmetric or azimuthally symmetric. In this case, when we rotate the system about z-axis, we see that system remains invariant or rotational invariant. That is, phi going from phi plus phi naught would not change the system. So that is one of the important class of symmetries which are extremely useful. And the most general case is when you have psi is a function of all variable r, theta and phi. That is a case we will handle a little later. Let's look at the azimuthally symmetric system first. In this case, it is equivalent to taking m is equal to 0, and in our earlier expansion e power im phi, because system doesn't depend on the phi at all. So our partial differential equation becomes independent of phi. So we have r into d square by dr square r psi plus 1 by sine theta d by d theta into sine theta d psi by d theta is equal to 0. Now we have to separate them using the orthonormal function. So we have already seen that the eigenfunctions are r to the power L and r to the power minus L plus 1 with the eigenvalue L into L plus 1. So we have psi as given some n going from L going from 0 to infinity, r to the power r L into PL of theta. Now we need to substitute this in our differential equation and simplify it further. So what we have is some L going to 0 to infinity, RL 1 by sine theta d phi by d theta sine theta into dp L theta of by d theta into L plus 1 p L of theta into r is equal to 0. So this equation is satisfied only if the coefficients of RL become 0 for each value of L, because of R of L are eigenfunctions of the differential operator and they are linearly independent functions. So now we set the coefficients to be 0. For each value we get a differential equation. We get an ordinary differential equation in theta. And that is 1 by sine theta d by d theta sine theta into dp by d theta plus L into L plus 1 into PL of theta equal to 0. This L into L plus 1 is coming because of the eigenvalue of a radial eigenfunction R of L. So this is often looks strange when we use a separability. Sometimes we use some combination, sometimes we use some other combination, which all look strange. But in this approach, we see that they are all coming because of the eigenvalues, and each of these combinations has a meaning as given by the eigenvalues. So in this case, we have a combination L into L plus 1, which is naturally coming because of the eigenvalues of radial eigenfunction. Now we need to solve this equation, or we see whether we can simplify it further. This is not in the form which we are interested in, so let's try to make a change of variable. Here we substitute x is equal to cos theta and relook at the differential equation. Now we substitute x is equal to cos theta, then sin theta becomes square root of 1 minus x square, and d theta becomes minus dx by square root of 1 minus x square. Now when we substitute back this in the differential equation, we get d by dx is equal to 1 minus x square into dp by dx plus L into L plus 1 into p is equal to 0. So this is a differential equation which we are interested in, and that is already in the Stern-Liouville form, and the domain for x is here minus 1 to plus 1. So this differential equation is a named differential equation, and it is called Legendre's differential equation. In the table of differential equation, this is called the Legendre's differential equation. Now this differential equation is not in the standard form. We have it in the Stern-Liouville form. We can simply write it down in standard form. It is straightforward to write this differential equation in a standard form. However, we have seen that given this standard form, writing back into Stern-Liouville form may not be always trivial, but in this case it is not that difficult either. So we have this differential equation in the standard form, which is a d square p by dx square minus 2x by 1 minus x square dp by dx plus L into L plus 1 divided by 1 minus x square p is equal to 0. Now it is straightforward to see that there are two singular points at x is equal to plus or minus 1. Both of these are regular singular point. It is straightforward to see we have a 1 minus x square in the denominator, which can be written as 1 plus x into 1 minus x, and both are simple pole at x is equal to minus 1 and plus 1. So this is a regular singular point. Can have a power series solution for the Legendre's differential equation. Let's quickly look at the power series solution for Legendre's differential equation. We write the equation in the standard form, which is a d square y by dx square minus 2x divided by 1 minus x square dy by dx plus L into L plus 1 divided by 1 minus x square into y is equal to 0. We see that x is equal to 0 is a regular point, and then we can have a power series solution at x is equal to 0. Since it is symmetric about x is equal to 0, the solution would be valid or convergent all the way till x is equal to plus or minus 1, excluding the point x is equal to plus or minus 1. Now we see that if we use the regular singular point, then we can also have a power series expansion around x is equal to plus or minus 1. Since they are already on the boundary, most of the domain can be simply handled by the power series at x is equal to 0. It is natural to study this differential equation with the power series at x is equal to 0. Exceptional cases, when really want the value of the points on the boundary, then one need to consider the point at x is equal to plus or minus 1. Because it is a regular point at x is equal to 0, the solution is much simpler than the solution which is comes at a regular singular point x is equal to plus or minus 1. Now we have seen in our standard technique, we expand P of x and Q of x in terms of power series or Taylor series, and then substitute for the power series. If we rewrite the differential equation in a slightly different form, we can avoid this Taylor expansion of P of x and Q of x, because they are already polynomials of sufficiently smaller power. It can be handled without doing the Taylor expansion. So we write the differential equation as a 1 minus x square into d square y by dx square minus 2x into dy by dx plus L into L plus 1 is equal to 0. Here advantage is that we don't have to now a coefficient in terms of power series. It is already a polynomial, and we can simply assume the solution to be in power series and substitute in this to obtain the solution. At x is equal to 0, we write solution as a y is equal to sum n going from 0 to infinity a n x to the power n. Note that we are not including the x to the power s, which is used only in the case of regular singular point. If the point is a regular point, then we simply use the power series. If it is a regular singular point, then only the indicial equation and x to the power s need to be multiplied. Here solution is regular and simply can be written as a power series given here. Now it is straightforward to compute the first and second derivative of this solution. Y prime is given as n going from 0 to infinity, n into a n x to the power n minus 1, and y double prime is given as sum n going from 0 to infinity, n into n minus 1, a n x to the power n minus 2. Now we need to substitute them back into the differential equation given in this form here, and then try to simplify. The first term here coming as 1 multiplied by y double prime, that is sum n going from 0 to infinity, n into n minus 1, a n x to the power n minus 2. The second term, which is coming here, is a minus x square into y double prime. That is why there is a minus sign, and n going from 0 to infinity, n into n minus 1, a n x to the power n. That x to the power n minus 2 becomes x to the power n, because we are multiplying by x square. Next term is coming because minus 2x is multiplied to y prime. That is we have it here as a minus n going from 0 to infinity to n a n x to the power n. Here x to the power n minus 1 become x to the power n because of the multiplication by x. And the last term, which is a L into L plus 1 into y, is given as a n going from 0 to infinity, L into L plus 1, a n x to the power n. Now it is important to note that the three of these terms have a very common pattern. They are all starting from n is equal to 0 and to the infinity, while they all have a x to the power n. So they are all similar, so we can combine them all. But the odd man out here is a first term which start from n is equal to 0, but it has a power x to the power n minus 2. So this term need to be further simplified in order to combine with the other terms, so that we can write a general expression for the coefficient. So let's try to rewrite. First, observe that first two terms here are 0 because we have n into n minus 1. When n is 0, this term becomes 0, and n is equal to 1, this term becomes 0. So those two are not relevant, so we can start from n is equal to 2. So this series can be written as n going from 2 to infinity, n into n minus 1 a n x to the power n minus 2. So since the n is a dummy variable, we can always start them wherever we want and suitably adjust the term. In this case, we start n from 0 instead of n is equal to 2, and then add 2 for each of these terms, so that inside this term all the n are replaced by n plus 2. So that is to say that the term becomes n going from 0 to infinity. The first n becomes n plus 2 because we are starting from 0, and the second term n minus 1 becomes n plus 1 because of again n starting from 0, a of n plus 2 into x to the power n, because we have to add 2 to each n. So now the term is in a very convenient form. We can see that it is also start from n to 0, and it has a x to the power n as the rest of the term. So we can easily combine them and to write them as this messy term. Though it looks like a messy term, you can see that n going from 0 to infinity, n into n plus 1 into this is n is equal to some n going from 0 to infinity, n plus 2 into n plus 1, a n plus 2 into x to the power n, and the rest of the terms are all n going from 0 to infinity and a n x to the power n. So this term now can be combined and written as a single term, which goes as n going from 0 to infinity, n into n plus 2 into n plus 1, a n plus 2 minus n into n minus 1 plus 2n minus l into l plus 1 a n x to the power n is equal to 0. Now most of the time this power series and substitution and simplification looks like a trivial non-intelligent job, but one of the important trick is to able to adjust this power series after substituting in the differential equation, and able to write them from n is going from 0 to infinity and x to the power n, so that the entire terms can be combined in the neat form and written as a single power series with the coefficient and x to the power n. If we are not able to do it, then it is often very difficult to get the clean recurrence relation. So this is an important step in the solving a power series, how you combine different terms such that you can set x to the power n term to 0. So this equation is satisfied if and only if the coefficient of x to the power n is 0. So that is n plus 2 into n plus 1 into a power n plus 2 minus n into n minus 1 plus 2n minus l into l plus 1 a n is equal to 0. There is no x to the power n here. So this is essentially our recurrence relation, which connects coefficient n to n plus 2. Finally, in a simplified form, you have a recurrence relation as a of n plus 2 is equal to n into n plus 1 minus l into l plus 1 divided by n plus 2 into n plus 1 a n. So once you have given a n, you can easily find out a n plus 2 in substituting this. That is why it is called the recurrence relation, and we can now find out the entire set of coefficient and substitute back in the power series to get the solution. Now here there are some nice important properties to be noted. This is specific to Legendre's differential equation. Interestingly, in this case, even and odd series get separated out because we have a n is related to an plus 2. So this makes it odd and even series get completely decoupled. Suppose you have been given a 0, your starting point of the power series, then you can find out a2, a4, a6 and so on, but you will never be able to find out a1, a3 and so on. This has to be set to 0. On the other hand, if you have given a1, then you can easily determine a3, a5, a7 and so on. You will not be able to determine a0, a2, a4 and so on. In this case, even and odd series are completely decoupled, and you will have to give the two starting point a0 and a1 depending on the odd series or even series you want, or if you want both of them, then you can give both of them, but the two initial points have to be given to evaluate the complete series, not one as in the most of the differential equations. Now, another important point to notice here is that the series terminates. That means you can see that when n reaches the value of L, the numerator of this recurrence relation becomes 0, and all the an plus 2 after that becomes 0. That means the series terminates, and we have a polynomial as a solution to the Legendre's differential equation whenever L is an integer. So that is why these solutions are called Legendre's polynomial. So we'll stop here and continue with the next lecture and evaluate the sum of the Legendre's polynomial for different values of L and exploit their properties